lost you at it. Quick catch. So did you turn it on?
Yeah, it's on.
Okay. All right, well, last time we pretty much derived the a formula for Dirac's propagator, Feynman's propagator for a spin 1/2 field. And let me remind you what we got. We had mean value in the vacuum of the time-ordered product of psi L of x, psi dagger m of y, and what we got was minus the derivatives of derivatives multiplied by gamma matrices plus m beta, which is I gamma 0, gamma upper 0. That's an unfortunate notation now that I think about it. And then an integral d4q, this is an integral we've seen before, 2 pi to the 4th, minus I over q squared plus m squared minus I epsilon e to the iq, and I see in my notes I have x. This is really x minus 1. Okay, so that's the expression for the Feynman propagator for a spin 1/2 field. One can massage this in various ways. Does anybody have a question about it? Let me remind you that the time-ordered product here has an extra minus sign in it. In other words, when x is earlier than y, then psi L appears to the right, and an extra minus sign appears in the definition of the time-ordered product. That is to avoid having the definition be absolutely silly due to Fermi statistics. Because if, for example, this is, if, for example, you had, let's just take two fields rather than the field and its adjoint. If you had them at equal times, so Tx psi Ty, and you had this time-ordered product without without the extra minus sign, then that would give you psi of, say, Lm. This would give you Tx psi m Ty. If the times were equal, then this would give you a 1/2 plus a 1/2 psi m Ty psi L Tx. And what you can see is that would be just 0, because the anti-commutator of the Fermi field with itself at equal times is 0. If, on the other hand, you had a dagger here, then you'd have a dagger there and a dagger there, and then what we would be getting would be delta of x minus y, because the anti-commutator, well, I guess we haven't yet, we may not have discussed this topic, but in fact it would be a delta function times delta Lm, and it would be delta q of x minus y. So, in other words, we want to avoid the situation where the time-ordered product creates an anti-commutator. And so by putting in an extra minus sign, that's avoided and we don't get this. So that's basically what's going on. In other words, or to put it differently, the time ordering of Fermi fields is designed to just put them in time order, but when you put them into time order, you have to respect the fact that they're Fermi fields, and so if you interchange one with the other, you're going to get a minus sign. So that's probably the best way, the better way of saying it. Now, there are many ways of writing this thing. One never writes it this way, actually. This is just the way one derives it. You let the derivatives act on this thing, which is, this thing, by the way, is to the right here. This is minus I delta F of x minus y. You let the derivatives act, and these derivatives are always x derivatives. So in fact, in many of the equations in Weinberg and in my notes, all derivatives are with respect to x rather than y, unless it's explicitly noted to be a y derivative. Anyhow, this comes in and differentiates with respect to x. That pulls down iq's, and so the result then is that the time-ordered product of psi L of x, psi dagger m of y, mean value in the vacuum, which is sometimes written as capital delta Lm of x minus y. This is then minus I integral d4q over 2 pi to the 4th minus I qa gamma a plus m beta over q squared plus m squared minus I epsilon, and then e to the iq x minus y. I see in the notes I consistently use x rather than x minus y. That's because I moused things in from earlier expressions. Now, what some people do is they say, well, minus I qa gamma a plus m minus I qb gamma b plus m. Well, this turns out to be q squared plus m squared. So you can imagine that this thing is the product of these two, and then you can cancel the numerator. And in fact, these two terms commute with each other. And so what some people do is they write this as minus I integral d4q 2 pi to the 4th e to the iq x minus y over I qa gamma a plus m minus I epsilon. But then you have a beta, and then the whole thing, you take the Lm matrix element of it. I don't know if there's any utility to doing that. I can't remember ever having made use of that expression. Some people write it down because they think it's cute. All right, so any questions? Yes.
What basis is this matrix element? What basis is this matrix element? What are the element basis states? You said it's like a matrix element?
Oh, well, yeah. I mean, here, we've got the
Oh,
L is an index going from 1 to 4.
Okay.
M is an index going from 1 to 4. These are Dirac indices. And beta is a 4x4 matrix, so is gamma. Or better yet, why don't we use this, which is less, this is sort of a magic formula. This is more conventional. Here, I forgot to say that we're taking the LM matrix element of that. So this is a 4x4 matrix.
Okay.
Take the LM matrix element.
This isn't like we have some operator going.
Huh? Okay, so, yeah.
I was wondering, so whenever you're writing QA gamma A, are you only summing over spatial components, or are you also summing?
No,
Okay.
I'm trying to use this notation where I, J, K, N are spatial,
Okay.
and A, B, C, X, Y, Z, and so forth are Lorentz, or 0 to 4. But in fact, this is just going from 1 to 4. These are the indices.
Yeah.
You know, it's...
Sure. So whenever you write q squared here, this is actually 4 vector q squared.
Yes, q squared is q 3 vector squared minus
Yeah.
q0 squared.
Okay.
Okay, you ready? All right, so that's the formula. Now what I think I should do is show you how this works in the calculation we did a few, I guess, last week or maybe the week before, when we were talking about a theory, and the theory that we had a Hamiltonian density. This is just the interaction part of the Hamiltonian density. GLM psi L dagger of x, psi m of x, phi of x. Weinberg considers something more general. He puts an index k on this and gives G3 indices, and I thought, well, that is more general, and I thought, well, we don't need that much generality. On the other hand, it's a nice, as he says, if you do add an index k here and an index k there, then what you're dealing with is an interaction so general as to be as to be able to represent any of the interactions of fermions with bosons in the standard model. But I don't think we need to be that general. So we went through this a few times ago, and I think we got this far, that we said that the amplitude for fermion-boson scattering, so that would be, we would have let's see, this has, yeah, right. Oh, sorry, I'm going to use a dotted line, I think, for bosons, and actually, no, this is a bad picture here. This is in second order, so what one has is this. And the boson can come in here and go out there, or you can have the same thing, but now have it go out there and come in here. And we can consider this to be P and K, and this is P prime, K prime. And in the notes, I go through this in detail, and I think we did it in class. Do you want me to repeat any of it, or? I'm not sure. I think maybe I should just pick up where I think we left off. If you add these two amplitudes together, what you get as the amplitude is minus GLM, GL prime M prime, U star L, of P prime S prime, U M prime of P and S, actually, if you choose your index labeling carefully enough, you can do it this way. LM, L prime, M prime. Oh, this is an L prime then. Right. Okay. And then you have integral d fourth x, d fourth y, e to the I, k plus p, well, let me rewrite this. E to the I, px, minus I, p prime y, minus I delta m prime L of y minus x. E to the I kx minus I k prime y plus e to the I ky minus I k prime x. Okay, and there are factors here, namely 2 pi to the 6th, and then square root of 2k prime 0, 2k 0. The other square root of 2 energies are hidden in the u's. So you're about to ask a question.
Yeah, I was more so just going to ask a question about these Feynman diagrams. Yeah, so I was wondering, like, so the vertices represent 2 different points in space, right? Like the 2 different.
Yeah. Well,
so
you can look at it in 2 ways. There are space-time Feynman diagrams and momentum space Feynman diagrams, and you can imagine that this is vertex x or y, and this is vertex y or x, and since you can interchange x and y, that gives you a 2 that cancels the 1 over 2 factorial. So you just wind up with this after you pick x or y. And so at this vertex, you have psi dagger psi phi, and psi dagger psi phi at this vertex. And then you can either choose to have both particles absorbed at the same vertex, or the 2 incoming particles absorbed at the 2 different vertices.
yeah, that just seems like weird. I mean, is it so the second Feynman diagram sort of corresponds to some like long-range interaction that's happening between these 2 particles or something like that? Because it's like,
all right. Well, now that you bring up the question of range, that's quite interesting. You see this line here is the propagator. In fact, some people put arrows on the propagator. Now, what is the propagator? Well, it's this thing, right? And if we look at it, there's an m squared here. Okay. So, hold on, somebody is either running out of blood sugar or
I have a really quick question.
Yeah.
Which is the time axis? Is it going up or is it going?
Okay, good question, great question. Weinberg puts the time axis going up, and I think that that's a better choice than the more common choice of having it going to the right or the left. The reason is that the distinction between up and down is more obvious and clearer than the distinction between left and right. And notice what's going on here. In this case, you can imagine that the two incoming particles get absorbed at one vertex in space-time and then at a later time get emitted. But we're integrating over all x and all y. So the two can be emitted before, or at an earlier time than the incoming particles were absorbed. So in other words, that's why I drew the thing horizontally rather than sloping up or sloping down. Because the time order of these two is, you have to consider both time orderings. And once again here, oh, I didn't get around to answering your question. This line here is the Feynman propagator. There's a 1 over m squared. And you've got a Fourier transform. Okay. So what does this tell us? This tells us that the values of Q that are important are when this thing vanishes. In other words, when Q squared plus m squared is either 0 or very small. And if the mass is huge, then the values of Q for which this thing will vanish are big. That means that this is a Fourier transform of a function that spreads out a great deal in momentum space. But then that means that when you do the Fourier transform, you get something that's localized in position space. And so that means the interaction is short range. So, on the other hand, if the mass is 0 or very light, then the interaction is long range. And so in particular for electromagnetic or gravitational interactions, it's long range. For the weak interactions, it's very short range. In fact, these interactions shouldn't be called weak interactions, they should be called short interactions. But people didn't learn that until 40 years after they were called weak interactions. It would be nice if we shifted and started calling them short interactions. Okay, I was going to say something else, but I've forgotten what it was. Well, all right, let me just go on. So the way, the detailed steps that lead to these two expressions are in the class notes for, it's sw5.pdf. Well, you don't have to, you just have to click on it on the website. And then it pops up as a PDF. Okay, now which term is which? In this term tells you that at vertex x, the fermion, which carries momentum p, is absorbed. And this exponential has kx in it. So this one is the first diagram. Whereas this one is the second diagram. And you can see that this is the second diagram because in this case, at x, you're creating the minus I k prime x is due to the creation operator of the scalar boson, and the I px is the annihilation of the incoming fermion. All right, now what we do, of course, is this minus I delta is this expression, minus I delta is the whole time ordered product, and it's this whole thing here. And so what we get is, well, first of all, this is y minus x. This one is x minus y. This one is Lm. And this one is m prime L. So you have to interchange x and y. You have to interchange L and m prime and m and L. If you do all that, what you find is that A is equal to minus G L prime M prime. No, yes, L prime M prime. GLM U star L prime at P prime S prime UM of P and S, and then an integral d fourth x, d fourth y, 2 pi to the 6th root 2k0 prime 2k0 e to the I ex minus I p prime y e to the I kx minus I k prime y plus e to the I ky minus I k prime x, and all of this times minus I integral d fourth q 2 pi to the 4th minus I, I'm going to use Feynman's notation, slash plus m beta over q squared plus m squared minus I epsilon. The I epsilon doesn't matter in diagrams like this. But anyway, this is m prime L, and then e to the iq y minus x. Okay, so that's our expression. The slash notation is a slash is a gamma a, which of course is the same thing as a gamma a. And remember, in the metric with 3 plus signs and only 1 minus sign, it's only the 0 component that flips sign when you raise or lower. This has a sort of nice, this looks nicer in matrix notation. You can imagine the G to be a matrix, and then if you do that, let me see if I can write it here. A then becomes this. I'm going to factor out the minus I. Becomes I integral d fourth x, d fourth y, 2 pi to the 6 root 2k0, 2k prime 0. I should have multiplied the exponentials together earlier. It would have made things clearer for everybody. That's one term plus and then all that is times integral d4th q pi to the 4th. And now, using matrix notation, it's U star, or in fact, it would be U dagger of P prime and S prime G minus I Q slash plus M beta GU of P and S e to the IQ y minus x, and then divided by q squared plus m squared minus I epsilon. The reason the I epsilon doesn't matter will become apparent in a few minutes. Okay, well now the d4th x, d4th y integrations, we can do them instantly, and when we do them, they simplify the expression enormously because they both lead to delta functions. And so what we get is that A is equal to I integral d4th q. Let me just remind you what the formula is. It's d4th q over 2 pi to the 4th e to the I qx is delta 4 of x. Or if it's y minus x, then it's y minus x. And so the delta functions use up 2 factors of 2 pi to the 4th, and we're only left with 2 pi squared. We can pull out another 2, and we just have to square root k0 times 0. The delta functions are delta of q minus k prime minus p prime delta p plus k minus q. And there are 2 terms. The other term is delta of p plus k minus p prime delta p minus k prime minus q. And this is then u dagger p prime s prime g minus I q slash plus m beta gu of p and s. Oh, my shoulder is giving out. Over q squared plus m squared minus I epsilon. I see there's a mistake in the notes here. Let me get rid of that. Okay, that's what we've got at that stage. And now you can see that if you do the d4th q integration, in the first term, q is equal to p plus k. In the second term, q is equal to p minus k prime. And so we get 2 different structures here. We get, also let me just do this. Okay. we get that A is equal to I, and then the leftover delta function is the same. It's P prime plus K prime minus P minus K. This is energy momentum conservation. The numerical factors are 8 pi squared, square root of K 0, K prime 0, U dagger of P prime S prime, the matrix G, whatever it happens to be, and now big parenthesis, minus I, P slash plus K slash plus M, over P plus K squared plus M squared. And the other one is minus I, P slash plus K prime slash plus M over P minus K prime squared plus M squared, beta G U of P and S. Okay. Now, if you do a number of, if you carry out this, if you do a number of Feynman diagrams, sitting down with your fingers, working through all the steps, you eventually come to realize how to write down this expression immediately. So people who actually do this for a living don't start the way I did with the amplitude, with Dyson's expansion, and move the fields and the operators around and so forth. They write this down immediately. And this then is said to be the Feynman diagram in momentum space. And you get to this by using what are called the Feynman rules. And Weinberg lists these rules, and I'll go over them explicitly on Tuesday. I think today I'd rather continue with something else, namely the propagator, the Feynman propagator for spin 1. After all, photons are spin 1, and so this is important. But basically, these Feynman rules are that you, of course, have an energy momentum delta function. These are the propagators for the two diagrams. This diagram here is this one. And so you have momentum P coming in, momentum K coming in. Momentum and energy are conserved at each vertex because there's a four-dimensional integral over each vertex. And the space variables always occur exclusively in the phase factor, the Fourier phase factor. So you always get energy momentum conservation at every vertex. So the momentum on this line is P plus K. That's why this is P plus K squared. This diagram here has P coming in and K prime going out. So the momentum here is P minus K prime. And then P prime goes out and K goes in. And that's why the Q squared here is P minus K prime squared. You can now check that if you have, this P is a physical momentum, K is a physical momentum, and you can check that if you have the physical momentum of a fermion of mass m, and the physical momentum of a boson of whatever the mass of the boson is, we don't need that. Let us call it mu. then this structure is never zero. And so the minus I epsilon doesn't play a role. So that's why, and the same, you can show that the same thing is true here. I think then the thing to do now is to start the analysis of the Feynman propagator for spin 1. And it's just a little bit trickier than the one for spin 1/2, but it's not actually difficult. So what we would start with is the general definition. Let me remind you of the general definition of what a so the propagator is the mean value in the vacuum of the time-ordered product. And the reason why this is important is that when you do this calculation, you start out with a vacuum on the left and a vacuum on the right. You take all the field operators and use them to absorb incoming particles, create outgoing particles, and what you've got left then is a time-ordered product of field operators between vacuum states, and so that gives you this natural. And this is theta of x0 minus y0, and it's a sum over s, an integral dqp over 2 pi cubed, UA of P and S, UB star of P and S, e to the I P x minus y, plus or minus theta of y0 minus x0, sum on S, integral dqp, 2 pi cubed, VA of P and S, VB star of P and S, e to the I P y minus x. So that's something that occurs in Weinberg's chapter 6 and in the PDF of my notes. The plus sign is for bosons, minus for fermions, upper sign boson, lower sign fermions. I once, by the way, was teaching at Wesleyan and in Connecticut, and I was teaching some elementary physics courses, and so the student had to do a makeup exam, so I made it an oral exam, and we came to the apartment I was living in, and I asked him to explain something or other, and he said, fermions were named after Fermi, and bosons were named after boso. I hope he's doing well. All I know, he's CEO of Goldman Sachs now. Anyway, let's now go to the special case of a vector field. So I'm going to let, and for some reason I chose an upper index, I don't know why. This would be a sum S equals minus L, minus 1, what am I saying? Sum minus 1 to 1, QP, square root of 2 pi cubed 2p0, and we have EA of P and S, A of P and S, E to the I, Px, plus E star A, or EA star, which would be the curve of P and S, a dagger of P and S, E to the minus I, Px. Okay, I'm picking the case for a real spin 1 field. If it were a spin 1, a complex spin 1 field, this would be B dagger. Okay. And so what happens is if you take this expression for the field, and substitute it in here, well, what happens basically is that the U's, so UA is equal to EA over the square root of 2p0. We also computed what the spin sums were for a spin 1 field, and it is sum over S EA of P and S, EB star of P and S. I raise the indices on the blackboard, they're lower than the notes, but anyway, A to AB plus PA PB over M squared. So that's what the sum actually is. And as a result, then, the mean diagonal vacuum is the time-ordered product of, now I'm lowering them, psi A, psi B dagger of Y it's theta of x0 minus y0 integral dqp 2 pi cubed 2p0. Eta, of course, is the flat space metric, minus 1, plus 1, plus 1, plus 1. Eta AB plus PAPB over M squared EBI PX minus Y. And the other term is plus theta y0 minus x0. And just to save, I'll just write ditto e to the I p y minus x. Notice these are d cubed p integrals. And consequently, the p's here are physical momenta. That is to say, P0 is the square root of m squared plus p vector squared. And consequently, P0 squared is p vector squared plus m squared. So in this right-hand side of this equation, that's what the p's are. Now, these p's we can generate by differentiating with respect to x. We have x and y, but we're going to choose to use x. And if we do, let me do it this way, then this thing is equal to, the propagator is x0 minus y0 eta AB minus dAdB over m squared. And this thing here, to save my shoulder, this thing, dqp, 2 pi cubed, 2p0, this space factor, this is delta plus of x minus y. The second term is theta of y0 minus x0. It's also a to ab minus dA dB over m squared. And it's delta plus h1 minus x. Okay, so what we'd like to do, of course, is to take these derivatives and pull them to the left of the theta function, step function. There's no problem in doing that for the space variables, for the spatial derivatives. But there is, we have to be a little careful for the time derivatives. Now we had this problem for the case of spin 1/2 on Tuesday, but in the case of spin 1/2, we just had a 1p. It was linear. It was a p slash. So we only had one derivative that we were pulling over. So we had one time derivative that we were pulling across. And when we pulled across the one time derivative, that generated plus delta function of x minus y minus delta function of y minus x, and they canceled. That still is true today for the spin 1 case. So we can pull everybody across. The problem comes with the second time derivative. And so let me just, we can pull the second time derivative across, however, if we recognize that these are physical momenta. That is to say, p0 squared is p squared plus m squared. And consequently, we can say that d0 squared is actually grad squared minus m squared. Okay? In other words, if we, the part that's two spatial derivatives, no problem bringing it across. One time, one space, no problem bringing it across because the delta functions cancel. Two time derivatives, we say, it's not really two time derivatives. It's the spatial derivative squared and the m squared, because it's because the p's are physical, or as some people say, on the mass shell.
So there's two time derivatives, but there's two time derivatives are hitting this delta plus, and delta plus is the Green's function for the fine derivative equation.
Well, sort of. I mean, it's. I don't know if the delta plus is a. I mean, I don't know. I'm not sure. It's the Feynman propagator that's a Green's function. In other words, capital delta sub f is a Green's function for the Klein-Gordon operator. These guys are different.
Okay.
So, and delta f is theta of x0 minus y0 delta plus of x minus y plus theta y0 minus x0 delta plus of y minus x. Okay, so we must interpret the d0 squared here as grad squared minus m squared, because the p0 isn't a free variable. Whether it's must or may, I'm not sure. But anyway, we do interpret it that way. So we can then go to we can then pull everything across, and what we get is a to ab minus dA dB over m squared times minus I delta f of x minus y. And so what we have is vacuum time order product psi A of x, psi dagger B of y. Actually, there's no need to rush. I'm not going to run out of time. Minus I, A to AB minus dA dB over m squared integral d4th q over 2 pi to the 4th e to the I cubed x minus y q squared plus m squared minus I epsilon. Okay, that's what we've got. Where, sorry, d0 squared is actually grad squared minus m squared. So in other words, we should maybe put quotes around these guys to indicate that the second time derivative is actually grad squared. If you want, I'll write it this way: grad squared minus m squared. So just to repeat, this is a subtle point. The thing that's linear in time, no problem, we can just pull it across. The thing that's quadratic in time, since the p's are physical, we can interpret the quadratic time derivative as a gradient squared minus an m squared. We then pull it across, and so I have quotes around it. Okay. Now, we don't want to go through life, however, writing derivatives with quotes around them. And so what we have to do is we have to compute what the difference is between the real-time derivative and the thing with quotes. And somewhere here there's an I over m squared. I forget where, but all right, let's just. Why is, oh yes. We have minus I times minus, so that's plus I, 1 over m squared. So altogether we have to compute this. I over m squared, grad squared minus m squared, minus d0 squared. What's the difference when this acts on d4th q over 2 pi to the 4th, e to the I q x minus y over q squared plus m squared minus I epsilon? Well, the amazing thing is that this is a very simple result, because this is just I over m squared. Grad squared brings down minus p squared, so let me just write the d4th q, 2 pi to the 4th, e to the I q, x minus y. Remember, we're differentiating with respect to x, not y. I wrote the exponential, it's there, but I put it in the wrong place. I want it here. And I'm going to write q squared explicitly. It's q vector squared minus q0 squared plus m squared minus I epsilon. Okay, now, grad squared. The grad squared pulls down minus q squared. The m squared is minus m squared. The d0 squared pulls down a plus q0 squared. So now you see that this is a fancy way of writing minus 1. Okay. And so this is equal to minus I, or plus I, yeah, minus I over m squared times d4th x over 2 pi to the 4th e to the I q x minus y. Well, maybe I'll write it explicitly. d4th q, 2 pi to the 4th, e to the I q x minus y. And so that is just minus I over m squared delta 4 of x minus y. Okay, so the difference of the two is a very specific thing, and so now we can write the Feynman propagator finally without quotes. We can say T of time order product psi A, psi B dagger of Y is minus I integral d4 q 2 pi to the 4th a to ab plus pa pb over m squared. Let's see, did I skip something here? Well, you know that minus I delta f is this four-dimensional integral. Yeah, I skipped a step here, I can see. So, let me do the skipped step here. What we've got is, let me just not skip a step. So what is this thing? This thing is A to AB minus dA dB over m squared times integral d4 q. Let me just make sure I've got, it's a minus sign. 2 pi to the 4th EBIQ x minus y over q squared plus m squared minus I epsilon. This m, by the way, is the mass of the vector boson. But we have to add the correction term, and the correction term is this, which puts back in the quotes and subtracts the d0 squared term. That and so if we do that, we have minus I over m squared delta 0a delta 0b delta 4 of x minus y. And the reason for that is that this PAPB refers to the indices, the Lorentz indices on the vector boson. And so it's only when both of them are time components that we have to deal with two time derivatives, which we then have to interpret as grad squared minus m squared. Okay, so this is the actual expression, and what that means is we have something that is manifestly Lorentz invariant. And then we have something that is awkward. It's not Lorentz invariant and embarrassment. Now, it turns out that this that the cure for this embarrassment occurs naturally, and we'll see how that comes about in Chapter 7, and in particular for the case of quantum electrodynamics, where the vector field is actually has mass 0, and it's the photon. What happens is that there's a Coulomb term, the instantaneous potential, that produces a term in the Hamiltonian that's an embarrassment, especially when you teach freshman physics, or sophomore physics, or maybe even junior physics. You have that term that's an instantaneous action at a distance. When you add that term in, that cancels this term. So what was an embarrassment when you look at Coulomb gauge electrodynamics is the term that cancels this and leaves you with a Lorentz invariant propagator for the photon. Now, to show you that in more detail, I'm going to go to the whiteboard and we've got 10 minutes, which is about as long as, more than we need to talk about this. But does anybody have a question, though? Okay, let me grab this. So this awkward second, suppose that so far we've just said we were interested in in analyzing what the Feynman propagator is for a spin 1 field. The way spin 1 fields normally interact is this way. They normally interact with currents, a current JA, and so then this is a 4-vector, that's a 4-vector, the dot product is a Lorentz invariant quantity. And so this thing is, so let's just say that if this is the term, if this is a term in the Hamiltonian, then if you do Dyson's expansion in second order, you're going to get something like this. And I'm not going to try to justify every exact factor, but you're going to have a minus I JA of X minus I JB of Y. And then you're going to have the mean value in the vacuum of the time-ordered product of the two fields, psi A with psi B. And that's going to give you the Lorentz invariant term plus this awkward term. And so I'm just going to put in the awkward term now. Minus I over M squared, delta 0 A, delta 0 B, delta 4th X minus Y. And we integrate d4th Y, or if you want, we integrate also d4th X. And so this thing is really an integral d4th X. Well, this delta function gives us a term. This gives us I J0 of X squared integrated d4th X over 2m squared. No, it's I times that. Yeah, I over 2m squared times that. So, as I said, the Coulomb term that is an embarrassment when you discuss quantum electrodynamics in the Coulomb gauge, or if you're dealing with with a massive vector boson, you naturally encounter a Coulomb-like term where the interaction density is in fact J0 of X squared. Notice J0 is just the charge density. So that's the Coulomb interaction, the charge density squared. And over 2m squared. And so what happens is if you have then minus I times that, you then have minus I times this. This term cancels this term. So everything cancels. In other words, it all comes out in the wash. I think, though, that this is a sign that quantum field theory isn't the whole story. You remember I said at the beginning of the course that quantum field theory is almost content-free in that the idea is you just are trying to describe particles scattering off each other in ways that obey special relativity and quantum mechanics. And there's apparently something else going on. And I guess nobody really knows what it is. For the last 40 years, we've had more. People have been advancing string theory as the right answer. And one of the more recent developments in string theory is that people have realized that if you take a quantum field theory and couple it to gravity, you can, of course, do that in a zillion ways because there are a zillion possible quantum field theories. Well, it turns out that of all this space of quantum field theory, the set of quantum field theories that, when coupled to gravity, are the low energy limit of a string theory, it turns out that this is, so to speak, a set of measures zero. That is to say, almost every way of coupling quantum field theory to gravity cannot be realized as a low energy limit of string theory. And so there are, at this stage, of course, nobody really knows for sure. The string theorists say, well, string theory is probably right, and so that means that we can use string theory as a guide for quantum field theory. And certainly I think we need a guide because obviously producing this awkward thing that somehow mysteriously is canceled when you go through the Lagrangian approach. A term develops that cancels this unwanted thing. I mean, that is pretty awkward. And then we've got all these infinities that occur. I mean, there's so many things that are problematic in quantum field. And as I said, it's almost content-free. What string theory theorists are saying is they've got the content. And that content, when you add it, eliminates almost all quantum field theories and narrows you down to a set that's infinitely smaller than you started with. Whether it's unique, I don't know. As an example, I might tell you one example. I've been listening to Vafa's lectures lectures he gave at Colorado in 2017. TASI lectures, they're available on the internet. Just Google TASI 2017. Anyway, one of the things he mentioned was you take a theory that's quantum field theory with global symmetry, and before Yang and Mills invented local symmetry, people thought that global symmetry was the normal one, and there was just something weird about quantum electrodynamics that had a local symmetry called gauge invariance. Well, it turns out the string theorists tell us that you can't if you couple a theory with global symmetry, but not gauge symmetry to gravity, you get something that can't be realized as a low energy limit of string theory. Of course, string theory could be a crock of poop. But on the other hand, if string theory is the way to go, then it's telling us that there are fewer quantum field theories, and that's the content that we've been missing. I wish there were I wish somebody would tell me where there's a good treatment of string theory. All the treatments that I've seen are ones where one would be reading and working through chapter after chapter after chapter of string theory before getting anywhere near understanding anything. So I don't know if any of you know of a good book on the subject or a good set of lectures, let me know. So any questions? All right, let's turn it.